Let's move on to example 5.2. In example 5.2 is cycloid motion. The motion which is represented in this figure is called the cycloid motion, which is a semicircle type of motion. Now let me read the statement of the example, and it says that a more exotic trajectory occurs if we include a uniform electric field B, uniform electric field E at right angle to the magnetic one. Suppose, for instance, that B points in the x direction and E points in the z direction, as shown in figure. A particle at rest is released from the origin. What path it will follow? So look here first at the situation. We are having a charged particle which is at the origin, and this charged particle will experience, means E is along the z-axis and B is along the x-axis. So one thing is sure, that electric field will apply force in the z direction and magnetic field will apply force perpendicular to the x direction. So perpendicular to the x direction are two directions, one is z and the other is y. But look, when it will go along this direction, so it means v is along this direction. So v along this direction and x along this direction. So the magnetic force will be along the y direction. So I can draw this, that the electric force which is here, the electric force will be, if E will be in this direction, this is the electric force, while the magnetic force will be in this direction. This is the magnetic force. It will be in this direction because V is in that direction. Now let's assess the situation, that what path it will follow. So it will see, look here. Is the particle is here, it is at rest. So the rest particle will have zero magnetic force. It will have only electric force. So the electric force will start moving it in this direction. And as it starts motion, means as V will occur, then this V will cause the magnetic force to start, because magnetic force is QV cross B. So instantly as we start, magnetic force will start as well, and the direction which was exactly this direction will get compromised, like it will start moving. If both the forces are equal, it will exactly start in the mid of this direction. But we know that as it speeds on, then magnetic force will increase. And what will be the result? The result will be slightly tilted motion, and that it will further tilt as the electric field will be accelerating the particle, and this tilt will go on until the magnetic force becomes almost equal to this thing. Then the magnetic force means after this point, it will start moving against the electric field, because at this point we have a balance. And after this point, if we resort in components, then the particle will be going against the electric field, and the magnetic field would like it to move it in a circle. So it will go against the electric field, and as it starts going against the electric field will resist this motion, and its speed will decrease. And as the speed will decrease, the magnetic force will decrease. So finally it will come to this point, and at this point the electric field will take over, and almost it will means the velocity will be decreasing, and finally it will come to rest, and magnetic field at point A will become zero, while the electric field will now start again here, because now the magnetic force is not there because the particle has got to rest, and this process will be initiated again and again and again, and the particle will be ultimately moving in the y direction, and this motion we call is the cycloid motion. So let's start. This is one of the descriptive thing. Let's now quantify the things that how we can uh, write the equations for this motion. We know that there is no motion along x-axis. The motion is in the y and z plane. So we have the displacement or the position 0 and x-axis, and then this is y of t and z of t. They are the time derivatives, time dependent displacement y a z. This is for position. I'm writing for position x. You can write r if you want. Then we have velocity. Then what velocity will be? Velocity will become the derivative of this with respect to time. So velocity will be, I'm writing y dot is per your book in z dot here. And the acceleration will be 0 and y double dot in z double dot. So we have the position, we have the velocity, and we have the acceleration. And now we are in a position to calculate the magnetic force. So first calculate the magnetic force, first calculate V cross B. The V cross B in a determinant form is the cross product. We do calculate X, Y, and Z unit vector. Then V is 0 and on X. Here it is Y dot and here it is Z dot. While B is only along x-axis, so we have D here, we have 0, 0 here. And this will give us the magnetic, the V cross B is, if I do the x-axis, then it is 0. This is 0 minus 0. For the y-axis, I will cut this one and this one. So 0 minus this bz dot, but 1 minus of the y. So it will become bz dot. It will become plus bz dot. And this will be in the y direction. Then plus we have, with this will be cancelled and this is cut, so we are left with this multiplied with this, which is by dot, by dot in the z direction minus 0 here. So we have bz dot and by dot in the z direction. Okay, we will have to take care of the sign here because when it is cut here, then we have 0 minus by dot. So here we have minus not plus. This is minus. And now we write the F equals Q and V cross B is bz dot and y minus dy dot and z, and we have, this is the magnetic component, and then we have Q and E the electric component, and E is basically in the z direction. So later on I will put the z direction here because we know the electric field is in the z direction. So we have E in the Z direction. Then this force is balanced by the centripetal force, or this force we can write, for example, Ma. Then m times mass of the particle in acceleration. And acceleration, from here we know that this is y double dot in the y direction and z double dot in the z direction. So we have from here the F equal to ma we have applied here, that F equals m is the force which is balancing this motion, and we have the components here. So the E component, E is in the Z direction, and we have from here, let me write it first and then E G Z dot in Y direction minus B Y dot and Z direction, and Q will come with this, plus E times E, and this E is in Z direction, equals to, this will be the acceleration, so it will be multiplied with n. So n in y double dot in y direction in n, and z double dot in z direction here. Now we can write the components, like the y component here and the y component here. Similarly, the z components here and the z components here. So this is equal to that QB z dot is equal to n y double dot in minus QB, so I can write it QE minus QE and y dot, and this is equal to mz double dots. So this is the y component and this is the z component. And now if I do write this thing, is this is equal to, if I look here to this equation, then QE minus this QB or N is coming with both of these. So I can write that this is, this I can write is QB over N, QB over N, and this is Z double dot equals Y double dot. Similarly here, if I divide this one whole on M, then I will have, this is Q, and if I do multiply this with QE and this over M minus QB over N Y dot, and this is equal to Z double dot. Now if I look at this one dimensionally, that what this QB over N is, QB over M, I know that Q is in coulomb, while B, if I don't remember, then a very typical equation like B equals mu naught I over 2 pi r. From this equation I can write its dimension. This is Newton per ampere squared, and I is an ampere, and then we have the meter here. So this is equal to Newton and 1 ampere is known. So Newton per ampere meter. Newton per ampere in meter. So we have this is Newton per ampere in meter, and here we are having M and M we are having in kg. So the dimensional analysis I'm doing that how this is what this comes out to be. Now here this I know that this is coulomb and Newton is kilogram meter and per second square, while ampere is coulomb per second. N is here, and then we have kg. So look at the coulomb is gone with coulomb, 1 second is gone with this second, m is gone with m, kg is gone with kg, and we are left with 1 over second. And 1 over second is basically unit of frequency. So I can define this QB or M is omega. And this is the frequency. Omega we define is QB over M. We define this thing. And this is frequency. Now this frequency, this is the frequency with which the particle would be going in a circle in the absence of electric field. Only the magnetic field is doing the job. And this is the frequency, the cyclotron frequency with which the particle will be going in a cycle. So here I can write for QD or N, I can write that this is omega z dot. Omega z dot is equal to y double dot. And here, this is, now B is required here. So if I multiply this with B and divide with B, then QB over N I will write as omega, and this will become E over B. So omega E over B, and then minus omega QB over M, and Y dot is equal to Z double dot. So we have the equation is in a simple form is Y double dot is equal to omega Z dot. We will solve this differential equation. It's a second order differential equation. Each, then this one I can write, if I write the omega is common, then Z double dot is equal to omega E over E. E will be minus and Y dot. So these are the two equations that I will solve, and this will give me the equation of motion of this particle.